So since I don't have your test graded today, all right, what we're going to do instead is we're going to start this new chapter. Actually get this recording to work. So what we're going to do then is on Wednesday, we'll have our quiz like normal, and then we'll go over the test. If you miss the test, because I honestly haven't even looked at the test yet, remember we will still have that one makeup test at the end of the semester. Okay, so if you miss the test, that'll be your chance to make it up, or if you just didn't do very well on one, that'll be your chance to redo it. Okay, the way the makeup test is going to work is I'm basically just going to put versions of all of our previous tests on Joule, have you print them off, and just do it as like a take-home test or a homework assignment. So I expect everyone to do really well on those take-home tests. I mean, there's no reason you shouldn't get 100 on those because you can ask any question you want.
Wait, hold on. So say that again.
We're going to have one makeup test, okay? And it's basically just going to be like a homework assignment.
Okay.
Okay? So you can ask me any questions you want. You can use your book. I'll give you about a week to do it. All right? So that's why I expect everyone, either if you missed a test or if you redid it, you'll have, that grade will be pretty good. All right? And I'll do this like probably the second to last week of class, a week or a week and a half before the final is when I'll pass this out again. Because remember, the final is going to be comprehensive. Okay? That means everything we've talked about so far is going to be on the final. So I want you to, if you missed a test or if you didn't understand a part, I want you to go back there and spend some more time on it. And that's what these makeup tests are really going to be. All right? So any questions about that? And that's why we spend so much time going over these tests. That's why on Wednesday we'll spend a half hour passing back tests going through it so you can see what you did wrong. Because even if that's not the one you want to redo, you're still going to need to know that information for the final. Now what we're going to do today is we're going to start our transition from physics to chemistry. Okay? How many people have taken chemistry before? Oh, look at that. You're taking it now, all right? Well, this should be a piece of cake for you then. No. But even if you haven't taken chemistry in a couple years, or really never, all right, we're going to go slow enough and kind of present it from a physics point of view to start with that it won't be that bad. Okay? So
that's for our book.
Yes, this is only for your book. Yeah. And so really, if you guys want, what we're probably going to get to today, we'll get to the nucleus and radioactivity, and we might get to nuclear reactions today. Maybe not. We'll see. Okay. Well, while you guys are writing this down, what do we know so far about atom? What are the three things found? There we go. Protons, neutrons, and electrons. And I'll just even put that right here, all right? Protons, neutrons, and electrons. What charge do protons have? What about electrons? What about neutrons? Nothing. Neutral. Okay, good. So that's our starting point. All atoms have protons, neutrons, and electrons. Okay, and so if we draw a pretty simple picture of the atom, okay, the protons and neutrons are going to be in the center. And of course, we have a special name for that center part, nucleus. Good. Okay. So in the center are the protons and neutrons, which is the nucleus. Okay. What charge does the nucleus have then? Positive. Because if we only have protons and neutrons, neutrons don't have any charge. Protons have a positive charge. That means overall, this nucleus is going to have a positive charge. Now, orbiting around the nucleus in all sorts of rings, which we're not even going to get into, quite honestly, okay, are the electrons. Okay? So for us right now, we can think about this on a very basic level as just having orbits where these electrons go. But really, it's not quite as simple as that because there's really just this region where we're going to find these electrons. Okay? And that is outside the nucleus. Protons and neutrons inside the nucleus, electrons outside. So far, so good, right? We can do this. Now, what we're going to use to help us understand all these different atoms is we're going to use the periodic table pretty heavily. Okay? Now, I know I've heard horror stories of other students saying they had chemistry in high school where they made them memorize the periodic table.
Yeah.
That sounds horrible and pointless to me. Okay? Really, what we're going to do is we're going to use the periodic table as a tool. All right? Periodic table has a lot of information on it. And so we're going to, in this class, learn how to pull out that information and use it. Okay? If we look at the one that's in your book or the one that's going to be on the wall here, right away we see there's probably a lot, even if you're taking chemistry right now, you might not know every little thing about. So what we're going to do is we're going to go one step at a time and pull out what we need to know until we hopefully understand most of it. But before we even get into that, the first thing we really need to do is try to get a better image of what an atom looks like. Because I don't know about you, but I can't see individual atoms. Okay? Individual atoms are very, very, very small. Okay? And so it's just not practical for us to have a microscope here that can see an individual atom. Really see an individual atom, you probably need a huge multi-million-dollar electron microscope, probably only one or two in the state, maybe at LSU. Okay? But even if we don't have those fancy instrumentation, we can still do a somewhat better job of visualizing what atoms look like. And really the first person to do this was Rutherford. Okay? This was back in the 1800s. Rutherford said, all right, we know we have a bunch of different atoms. We know those atoms have different properties. But why? All right, what do they look like? So he devised this experiment where he started with a thin sheet of gold foil. So imagine like aluminum foil you have at home, but made of gold. I don't know why he chose gold, but he did. Maybe he was rich. Okay? And so what Rutherford did was he took this box that was really a source of alpha particles, which we're going to talk about more later. But what we need to know now about alpha particles is they are smaller than an atom with a positive charge. Okay? So we took these small positively charged particles and fired them at this piece of gold foil. Now, what does common sense tell us is going to happen? If I have a solid particle and I fire it at a solid piece of foil, what's common sense say will happen? It's going to bounce off of it, right, or break through it. But really, I mean, if we can imagine it somewhat similar to me throwing a baseball at that wall, okay? Baseball's going to bounce off, right? And even if I throw it out the window, I'm not that strong. It's probably going to bounce off, okay? And what Rutherford found is that this happened, but really it was less than 1% of the time. For the most part, the vast majority of these just went straight through. Maybe close to 98%, probably even a little bit higher. What does that mean? If I threw a baseball at this wall and it went right through, what does that mean about the wall? Okay, there's a hole in it. The window's open, all right? Something like that. So what this means is that these atoms are mostly empty. Every atom is mostly empty space, okay? And this last 1% was just deflected a little bit. If we expand on this picture here, okay, of all these gold atoms here, we'll say it's a really thin piece of foil so that it's only a couple atoms thick. Since these pass right through, that means most of these atoms are just empty. What do you think happened to this 1% that bounced back? What do you think they hit? The nucleus. Okay? At the center of every atom is that nucleus. Now, since it only happened really less than 1% of the time, that must mean that this nucleus is very small. So they would have to hit dead on in order for it to bounce back. And then, just as likely, if we got too close to the nucleus, what's going to happen? If a positive particle gets too close to a positive nucleus, It's going to be deflected. So it's going to bend a little bit. So what this does is showed us that the vast majority of this is empty. The nucleus is very small right in the middle, but all that other area where those electrons are orbiting around is mostly empty. And if we look here, really, the neutrons and protons have a mass of about 1 atomic mass unit, which we'll talk about in a little bit. And the electrons are a lot smaller. So not only is this mostly empty space, but all of that mass is concentrated right there in the center. And really just to kind of bring this out a little bit, we can kind of visualize this. So if I took, let's say, a carbon atom, and let's say I blew up a carbon atom so big that its nucleus was the size of this screw. Okay? Someone guess for me, how big do you think that atom would be? If this was a nucleus, how big would that atom be? Quite large. That's good. It is quite large. No one wants to guess. Give me some. 3 or 4 feet. It would actually be as big as Sowella. So if we go from one end of the campus all the way to the other, that would be the size of the atom, and this would be the nucleus. Okay? This tiny thing would be where all the protons and neutrons are, where the vast majority of the mass was, and all that empty space around us would be the area where those electrons are orbiting around. But even if we think about carbon, that whole area is just where 6 electrons are orbiting around. Okay? So this nucleus is very dense and very small compared to the size of the atom. Now I mention this now because it's important to think about these things in order to understand what we're going to do in the future. What that means is that when I touch this desk right here, all right, I'm not really touching anything solid. What I feel here is really just the electrons in my hand, all right, this big empty area in the electrons, touching the electrons on this table. And what do we know when 2 negative charges get close to each other? They repel. So this electrical repulsion is actually what we sense as this touch. All right. Now I obviously can't push my hand through here because that repulsion is too great. But even for solid objects, the vast majority is just empty. That's kind of weird, right? Okay. But now that's true for every atom. But we still need to be able to tell one atom apart from another one. And so the first thing we can do when we look at that periodic table is that we can tell that we don't really use the names for all these atoms. Every time I talk about carbon in chemistry, I don't write out carbon, I use C. Every time I talk about nitrogen, I use N. Okay? So one thing that all these atoms have in common is that they all have a different symbol used to represent them. Now, most of these make sense, like C for carbon, P for phosphorus, S for sulfur. But some of them don't. K for potassium. What's PB? Lead. Okay. What's AU? Gold. Okay. Well, you get these weird ones because all these are based on the Latin names for these atoms. Okay. Now, since English is based on Latin, a lot of them make sense. Okay. But at the same time, I don't even know what lead is in Latin. Something I can't pronounce, I think. Yeah, I'm not even going to try. Okay. Same thing with potassium. Potassium in Latin starts with a K. So we get kind of these weird things. Now, once again, you don't have to memorize what these different symbols are for these different atoms. Because the periodic table in your book has all this. All right? But what we do need to know is that it's not going to be as easy as just taking that first letter from the name. It might be something different. Even if we think about something like carbon and chlorine. Both start with a C, but we already had carbon, so chlorine Cl. So that's the first thing. We have a chemical symbol. So let's start talking about carbon first. Okay. The other piece that's going to help us is the atomic number. Okay? So the atomic number, when I write out like this, I'm going to put the atomic number in the lower left-hand corner. The atomic number on the periodic table here is found in the upper right-hand corner. Okay? And the atomic number is going to tell us how many protons we have. So carbon has an atomic number of 6. That means we have 6 protons. Now what we're also going to do is we're also going to say that all these atoms start off being neutral. So if I have 6 protons, how many electrons do I have? 6. Good. Because those 6 positives have to be balanced out by 6 negatives. And finally, the last number we need to worry about is this mass number. The mass number tells us how many protons plus neutrons we have. Because remember, protons and neutrons are really where most of the mass is in an atom. So if we have protons plus neutrons, that's our mass number. So how would I figure out how many neutrons I have here? Yeah, so we just take 12 minus 6, so protons plus neutrons minus protons, and we get 6. So we have 6 neutrons here. Okay? So with the atomic number, mass number, and the symbol, we can tell a lot about the atom we're talking about. Let's try another one. Let's try this time chlorine. Chlorine 3517. How many protons do I have? 17, right? Yes, 17 protons. That means 17 electrons. Not 17 this time. It's 18, right? So it's 35 minus 17, so 18 neutrons. Okay. The protons and electrons are always going to be the same for a neutral atom. But the number of neutrons doesn't have to be the same here. It can be, but it doesn't have to be. Okay. And let's try one more weird one. Hydrogen 1,1. How many protons? 1. There's 1 proton, 1 electron. And then how many neutrons? 0. 1 minus 1, so 0. So for the most part, every atom is going to have neutrons, but they don't have to have neutrons. Practically, that means that hydrogen most commonly does not have any neutrons, and it's the only atom like that. Okay? How are we doing? Good? Boring? Seen all this before? Okay. Well, with the periodic table and this information, that means we should be able to get a ton of data about individual atoms. Okay? Remember, what we're doing now is trying to get everyone to the point where we can look at that periodic table and say 10 things about an atom. I can tell you right now, on the next test and probably on the final, I'm just going to say, tell me 10 things about bromine. And we're done today, well not today, when we're done with this chapter and the next chapter, we should be able to do that. Okay? But we can start off with just what we've learned so far, with things like the atomic number, mass number, number of protons, number of neutrons, number of electrons, and symbols. Okay. So if I make a not so crappy table real quick. Let's try a few of these. So let's say first I give you something that has an atomic number of 12 and a mass number of 25. Okay, let's just go around make sure everyone's talking today, and we'll see if we can figure this out. And I'm going to do horrible with names today, because I'm just not doing so well. All right. Carlin? Derek. I should have guessed Derek. This is a class with 5 Dereks. All right, Derek. If I have an atomic number of 12, how many protons do I have? 12. Okay. How many electrons do I have? I have 12. Okay. How many neutrons do I have if my mass number is 25, my atomic number is 12? 13. Good. What atom is this? If I look at the periodic table, what has an atomic number of 12? There we go. Okay, magnesium. Good. Not so bad. Let's try to make this a little bit more difficult. If I have 20 neutrons and 20 protons, what's my atomic number? Oh, now you're skipping ahead. Just because I don't know everyone's name, all right? So 20, all right? So it's Kevian, right? All right, good, all right. What's my mass number, Kevian? 40. Okay. Now, what's your name? Andy. Okay. How many electrons do I have? 20. Because my number of protons? 20. Okay. Kara, right? Calcium. Good. Okay. Let's make this a little bit different. My symbol's N, and I have 10 neutrons. Michael. If I have my symbol's N, so I have nitrogen, what's my atomic number? So remember, the atomic number is just going to be this number in the upper right-hand corner on the periodic table. Yeah, so, and if you look in your book, I think it's in a little different place, yeah. In your book, it's just right above it, okay? So the atomic number here is going to be 7, okay? What's your name? Chance. Okay, what else is 7? Protons, okay? What else is 7? Electrons. And finally, what's our mass number? 17. So just protons plus neutrons. Okay. Now let's do one more. Let's say this one's hydrogen, but this hydrogen has 1 neutron. Okay. Yeah.
What if 14 come in?
Now, we haven't got there yet. Okay. So this number right here might look like the mass number, but it's not. Okay. It's tricky, I know. Okay, Zoe. Let's finish up this last one. If I have hydrogen with 1 neutron, what's my atomic number going to be for hydrogen? 1. Okay. And Derek again? Right. Feeling good. What else is 1? Protons and electrons. Okay. You must be Carlin, right? All right. Carlin, what's the mass number here? Don't look at the periodic table. The periodic table is going to trick you. If I have 1 proton and 1 neutron, what's my mass number going to be?
You subtract those, right?
Now we're going to try to find the... Not 1. 2, right? Because the mass number is protons plus neutrons. So the mass number here is 2. Okay? Now, those first 3 homeworks I'm going to give you are going to be more practice on this. Okay? Well, let's just try on your own. Try and do 2 more, and then we'll fill this in. Okay? And I know if you guys are sick of this, I'm sorry. All right. So let's say this time we have 10 neutrons and 11 electrons. And then finally, we're going to have a mass number of 30. 30 with 16 neutrons. So take a couple minutes and see if you can fill in the rest of those two. How do we do with this? Good? Bad? Okay. Let's just fill in these rests real quick. If I have 11 electrons, what else is 11? Protons and atomic number. Yeah. So really, a lot of things are going to be 11. Okay. What's my mass number going to be here? 21. So just 11 plus 10. And finally, if I look at the periodic table, what has an atomic number of 11? Na. Sodium. Yeah, it's another one of those. Na and sodium. I don't know. Okay. Here, it's kind of weird. 16 neutrons, 30 for a mass number. What's the first thing you can get here? Yeah. So 30 minus 16, that's going to tell us the number of protons we have, which is also the atomic number, which is also the number of electrons. Okay. And finally, what has an atomic number of 14? Silicon. Good. Good. Just remember, all right, this atomic number is going to tell us what atom we have. So sulfur is always going to have an atomic number of 16, all right? Nitrogen is always going to have an atomic number of 7. Krypton is always going to have an atomic number of 36. So that's always going to tell us what we have. Now that bottom number is going to trick you up sometimes, because what we're talking about so far are individual atoms, okay? So if I could look at one individual magnesium atom, if its atomic number was 12 and its mass number 25, they would have 12 protons, 12 electrons, 13 neutrons. But different atoms can have a different number of neutrons. So an isotope is an atom that has a different number of neutrons. And your book uses hydrogen as an example. These hydrogens, easy atom to start with.
What's that word?
Neutrons,
No, not the isotope.
different number of neutrons. Sorry. All right. So if we look at hydrogen, most hydrogen is hydrogen 1,1. So the atomic number of 1 means we have 1 proton, 1 electron, and then 1 minus 1, 0 neutrons. But some of the hydrogen floating around is hydrogen 2,1. What's the only thing that changes here? There's 1 neutron this time. There's still 1 proton, still 1 electron, but now there's 1 neutron as well. And there's even some hydrogen 3,1. Still 1 proton, still 1 electron, but 2 neutrons. So all 3 of these are still hydrogen. Okay? It doesn't matter if there's 0, 1, 10, a million neutrons. It's still hydrogen because it has an atomic number of 1 because it has 1 proton. The only thing that's changed is the number of neutrons. What does changing the number of neutrons do? What else changes? The mass. Okay, it changes the mass number, which changes the mass. So since there's no charge on these guys, the only thing that's changed is that you've made them heavier by adding in more neutrons. Now, this number down here isn't just one atom. This number right here is an average of every atom in the world. Okay? So while if we look at hydrogen, most hydrogen atoms just have a mass of 1. But 1 in every 100 or 200 is hydrogen 2-1. So that bumps up the average to a little above 1. Okay? Let's take a look at carbon, for example. Carbon's relatively easy to understand. Carbon 12-6, like we already saw, has 6 protons, 6 electrons, and 6 neutrons. 99% of carbon is carbon 12-6. Okay. Now, carbon 12-6 also has a mass number of 12. Okay. That tells us the relative mass of carbon. Now, instead of using kilograms to measure this mass, we actually use this thing called the atomic mass unit. I'm just going to abbreviate that AMU. Now, why do you think we don't use kilograms? It's too small. Yeah. A lot of scientific notation is really a pain in the ass. Okay? If we look at this book is about a kilogram. This book is made of trillions and trillions and probably quadrillions of atoms. That means that each individual atom in this book is a tiny, tiny, tiny fraction of a kilogram. So instead of dealing with that nonsense, all right, we use these atomic mass units. And basically, an atomic mass unit, all right, is about equal to the mass of a proton or the mass of a neutron. Since they're about the same, we just say 1 proton is 1 atomic mass unit. 1 neutron is 1 atomic mass unit. So carbon 12-6 here, with a mass number of 12, has a mass of 12 atomic mass units. But now what about that other 1%? Well, most of the rest of that carbon is carbon 13-6. Still 6 protons, still 6 electrons. How many neutrons do we have now? 7. And so that makes up about 1% of the carbon. And carbon 13-6, with a mass number of 13, has a mass of 13 AMUs. So now if I wanted to find the average here, well really, if I don't even think about this, if I want to find the average of anything, what do I do? Add them all up and then divide by how many we have. Okay? Since I have percentages here, it's actually a little bit easier than that. Okay? Because all I have to do is say, well, I have most atoms with an atomic mass of 12. So that's 99% of the atoms found in nature. And the rest of them have a mass of 13. So if I just add those together, I should get what the average is. Anyone with a calculator want to help me out? What's 12 times 0.99? We have to be a little bit more precise than that. Yeah, 11.88 or 11.88. Yeah, we have to be a little bit more precise here since we're dealing with such small values. Okay, and then 13 times 0.01? Yeah, 0.13. So when we add these together, we get 12.01 AMUs. So the average mass of a carbon atom is a little bit over 12. Now this makes sense, right? Because most of it was 12, but we had a little bit that was higher. And if we look on our periodic table, that matches up well with this number here, 12.0115. So really we were a little bit off. What this number is, this is the atomic mass. So while the mass number just looks at one individual atom, The atomic mass is the average for every atom. It's saying if I picked up a handful of carbon atoms, that average mass would be 12.01. I'm not going to be able to pick up one carbon atom that has a mass of 12.01, all right? Because they're either going to have a mass of 12 or 13, but the average is going to be 12.01. How are we doing with that? All right. Why don't you guys try this next one for me? Chlorine, for the most part, is chlorine 3517. About 75% of chlorine is chlorine 3517. The other 25% is chlorine 3717. So while we're going to get a drink real quick, see if you can tell me what is the average mass of chlorine then, without looking at the periodic table. What did you guys get for this? 35.5. Why does that make sense? How would you know you're wrong if you got 34? Because the lowest number is 35. Okay? So it's always important to do a reality check here. Even before you start, we can look at this and say, well, the majority of it is 35, but we have a little bit that's higher. So our number should be a little bit higher than 35, but closer to 35 than 37.
What is it?
35.5. Because if we set this up, we start with that 35 times 0.75, and then we add 37 times 0.25. Okay? Then we add those up, we get 35.5 AMUs. And we can check ourselves again on the periodic table. Once again, we rounded a little too much, but we have 35.45 is that mass of chlorine. Okay? And remember as well, all right, not everything just has two different isotopes. Most things really have a bunch of different isotopes.
Why 37?
Why 37? That's a much more complex question than I can answer.
Like why wouldn't I have done like, why not 36?
Well, as we're going to see later, okay, these isotopes change the mass, but that also affects the relative stability of these different atoms, okay? So because of the way these protons, neutrons, and electrons are arranged here, okay, 37 is a lot more stable than 36. That's not to say 36 doesn't exist, but it's a lot lower percentage, okay? Because even if we think back to, go back to carbon real quick here. You haven't heard of carbon dating before? Yeah. Okay. Yeah, it's how you tell how old something is. And if we look, all right, 99% of carbon is carbon 12.6, 1% is carbon 13.6, but there's an even smaller fraction that's carbon 14.6. Okay? But that fraction isn't stable and it decays relatively quickly. Really, we can have carbon 106, all right? But while 99% of carbon is 12.6, there might be one carbon atom in the universe that's carbon 106. So that's why we just don't even worry about that. What we deal with here and what the atomic mass tells us is which of these isotopes is more likely to occur. Okay? So carbon 12-6 is much more likely to occur than all those other isotopes. But even if we have something, let's go to the next page. Even if we have something like, let's go boron. Okay. Let's say that most of boron you find is boron 11.5. Okay. Let's say 80%. But 15% we'll say is boron 10.5. And another 5% is boron 12.5. Okay. Really, you don't have to have these two equal isotopes. You can have all sorts of different varieties. What's the only thing we're going to have to do differently here to find the atomic mass? Yeah, I mean, we're just going to have 3 of them, but we're going to do the same steps we did before. Okay, we can do this together. We're going to have 11 times 0.8. What's that come out to be? 8.8. Yeah, so 8.8. Then we're going to have 10 times 0.15. What's that? Yeah, 1.5. And then 12 times 0.05, which is 0.6. So we still just add these up like we did before, and what we get is about 10.9 AMUs. Okay. And so that's really why all these numbers are more precise, right? Because there's not just 2 isotopes for carbon. There's not just 3 isotopes for boron. There's a lot more than that. And that's what appears in this average. If we skip ahead to some of these other ones down here in parentheses, all right, these are all artificial atoms. Okay? And so there's only one isotope that was ever made. So that's why it's in parentheses, because it doesn't occur naturally. Okay. Any questions about this before we move on? Okay. So what we're going to start talking about today, probably won't get done with, is this idea of radioactivity. Now, once again, I'm going to say radioactivity is a fancy word for something. Anyone know what radioactivity is a fancy word for? It has the same thing to do with radiation, yeah. But really, when we think about radioactivity or radiation, we think of something as being unstable. Okay. I know that sounds a lot, less imposing. Instead of radioactive man, you have unstable man or something like that, but still. Okay. Radioactivity just means that an atom or molecule, is unstable. And we can think about why this is. And this has something to do with those isotopes. If we start with the most basic atom we know, a hydrogen atom. Okay? Hydrogen atom has 1 proton in the center, in its nucleus, and 1 electron orbiting around. Okay? And so we say this guy is pretty stable because the positive from the nucleus and the negative of the electron balance each other out. Okay? It's pretty much just like planets orbiting around the sun, right? Because what would happen if the planet stopped orbiting around the sun? We'd all die, all right? But what would happen if I just had the sun and the earth? Seasons wouldn't change, but even something more basically, half would be hot, half would be cold, but only for a short while, because what would happen if I have 2 big masses right near each other? Yeah, they're going to attract, okay? So they're going to attract together and just Earth gets sucked into the sun. But because it's orbiting, we have this balance of these forces. So we have this force that's just constantly orbiting. It's the same way with electrons orbiting around a nucleus, okay? Because I know if I put a positive and a negative charge next to each other, they just attract, right? But here, since we have this orbiting, there's this balance of forces, okay? It's the same way with bigger atoms, but it gets a little bit more complex. So if we look at uranium, for example, okay? Uranium is a huge, huge atom. with 92 protons and a bunch of neutrons. So let's imagine for a second we do have a situation like this, where there's a bunch of electrons orbiting around here, but let's say at one point in time, all the electrons are on one side. And if we look at this small part here, with a bunch of these protons right next to each other, if you put a bunch of protons next to each other, what do you think is going to happen? They're going to repel, all right? These protons do not like being next to each other at all. So that's why we call this unstable. To make it more stable, a piece is going to break off. Okay? That's what we mean by radioactivity. When something's unstable, it wants to do something to make it more stable. And the way it does that is by having a piece break off.
So like releasing protons?
Well, there's one of three things that can happen. Okay? Here we go. Okay? There's three things that can happen to make an atom more stable here. It can either emit an alpha particle, a beta particle, or a gamma ray. And this is all natural, you know. There's uranium sitting in the ground right now. There's plutonium sitting in the ground right now that is undergoing this process naturally, okay, with no human intervention. All right? And really, in a way, it's pretty orderly. We have alpha, beta, or gamma. But now, back when people were first discovering radioactivity, okay, they didn't know what these things were. They just knew that some things were radioactive and some weren't. So what they did was they devised this experiment. They said, okay, I'm going to put some uranium in this container. And I'm going to have it so these three types of radiation are emitted from one side, but on either side I'm going to put a positive and a negative plate. So I'm just going to put an electric charge on them. Now, what they found was that alpha particles were deflected from the positive plate and attracted to the negative one. They found that beta particles, the opposite happened. In fact, they seemed more attracted to this positive plate and more repelled by the negative. And finally, the charged plates didn't seem to do anything to gamma. Nothing at all. What does this tell us? If we look at alpha first, if we have alpha particles that are deflected by the positive and attracted to the negative, what charge? It's positive. Good. So alpha particles have a positive charge. And in reality, alpha particles are just 2 protons and 2 neutrons. So they're really just the nucleus of a helium atom. Okay? What about the beta particles? If they're attracted to the positive but repelled by the negative, they're negative. Okay? And these negative particles are actually attracted more to the positive because they're a lot lighter. Beta particles are just electrons. And finally, what charges are going to be on gamma? Well, there's going to be no charge. Okay? And in fact, what they found out is gamma is just light. Okay? Remember those gamma rays we talked about when we're talking about waves? That's what we have here. Okay? And we know light doesn't have any charge. Light just passes through, nothing wrong. Okay? So we have alpha particles. That's my symbol for alpha. Beta and gamma. So either an atom can release a chunk of its nucleus, which is 2 protons and 2 neutrons. It can release an electron, or it can release just light. Really just relieve some energy. All right? Well, and this is where it depends. All right, depending on the atom, one is more likely than the other. Okay, so like for example, uranium, all three happen, but plutonium, for the most part, you're going to get more gamma and beta than alpha. Okay, but we don't need to know that much. But what we can do now is we can actually determine what's going to happen to an atom once it undergoes this process. Nuclear decay is what we call when an atom releases one of these. Let's start with uranium, because uranium's fun. Okay, uranium-238. Believe it or not, uranium is actually very common in the crust of Earth. Okay, uranium is found all over the place. Okay, and for the most part, the most common thing for uranium to do is uranium can decay by emitting an alpha particle. And remember, an alpha particle is just the core of a helium atom. So I'm just going to use He42 as my alpha particle. Now, what did we learn about energy? What did we say about energy? What was on this last test? It can never be created or destroyed. That's what I was looking for. Okay? Well, the same is true about matter. Okay? And once again, we're going to see some exceptions later on. All right? But we are not going to create or destroy matter in chemistry. We are just going to rearrange it. So if I have a situation like this, where I have uranium with 92 protons, and it loses a piece that has 2 protons, how many protons is it going to have left? 90. Okay. If it had a mass number of 238, lost 4, what does it have now? 234. Well, is it still uranium if it has an atomic number of 90? No. Thorium. Yeah, no problem. So basically what's happened here is that uranium lost a piece of its nucleus and became a new atom. In this case, thorium. This is an example of nuclear decay. All right. This is also a nuclear reaction. Okay. Call it nuclear because it happens in the nucleus. So we lost a piece here. And this right here, I'm just going to call my alpha particle. Now, when we talk about things being radioactive, we're not really done here. Okay? Because uranium was radioactive, it was unstable, so it lost a piece trying to get more stable. So it lost a piece and became thorium. But unfortunately, thorium isn't really stable either. So thorium is actually going to undergo another reaction. But thorium is actually going to decay by emitting a beta particle. Okay. Well, now I said a beta particle is just an electron, right? So what's my mass number for an electron, do you think? Think about this. What's my mass number for an electron? What is mass? What's a mass number? It's protons plus neutrons, right? Do electrons have protons? No. Do electrons have neutrons? No. So my mass number here is just 0. Now, this is where things get a little weird, okay? Because obviously an electron isn't a proton, but it does have a negative charge, right? So really we say that a beta particle has a -1 for its atomic number. But here the same rules apply, okay? We have to have the same numbers on the left that we have on the right. Okay? Here we have them in two different places. The same is going to happen here. So in this one, we have 234 on the left. That means we have to have 234 on the right. So what's my mass number going to be? 234. So nothing changed here because that mass number is 0. But now, if I have 90 minus a negative 1, what do I have here? Not 89. No. Yeah. I have 91. Okay. So if we look here, we have 90 and then 91 and a negative 1, so 90 over here. So we lost a negative 1, so we added 1. And I know that's weird. Okay. Yeah. Yeah. Really, the thing to keep in mind, no matter what's going on here, and this is going to help us when we go to our more advanced nuclear reactions, is that the numbers on the left have to equal the numbers on the right. Okay? So here, 92, 2 plus 90, 92. 238, 4 plus 234, 238. 234, 0 plus 234, 234. 90, negative 1 plus 91, 90. Okay? And once again, we look on the periodic table, what is this? PA. I don't know what that is. Okay. And finally, our last reaction, we'll go back to uranium here. Okay. Last reaction is really the easiest because last reaction is just a gamma ray. Well, if it's just light, does light have any mass? No. Does light have any protons or electrons? No. Okay. So what is going to come out? Yeah. So it'll just be the same thing.
So how are you supposed to know that?
Are you supposed to know what?
Like the beta and then gamma, how much?
Okay. You don't have to memorize what reaction is going to happen. What I'll tell you is I'll either give you that thorium decays with a beta particle, and you tell me what's coming out. Okay? Or, let's try this before we move on. We could do this the other way around. I could say, ooh, let's go to carbon-14. Okay? Carbon-14 is what we use to carbon date things. Okay? And so carbon-14 decays by emitting something and then turns into nitrogen 14-7. So I could ask you, what is it that comes out of that? Okay, you guys are too quick. Okay, yeah, so we just do the same thing though. We have to have the same numbers. So here I have 14 and 14. So that means my mass number is 0. But I have 6 and 7, so I need a negative 1. And remember, only those three things can happen. The nice thing about natural radioactive decay is you don't get anything crazy happening. You can't have one proton be emitted one time, all right, or 5 protons. It's always either going to be an alpha, beta, or gamma decay. And so the only thing that has a mass number of 0 and an atomic number of negative 1 is a beta. Okay. Why don't you guys try 2 of these real quick? Let's try a different one with uranium-235, 92. This one's going to emit an alpha particle. And then how about lead? Yes. Sorry. Okay. Remember, this is one of the nice things too, where my bad handwriting doesn't matter too much, because it doesn't really even matter what these are. Okay, what is important here are the numbers. Is done already? So what's my new mass number going to be here? 231. What's my new atomic number going to be? 90. So what? Thorium. TH. What about this guy? 4,2. And what's 4,2? He, which is just an alpha particle. Okay? Yeah, so remember, an alpha particle is just the nucleus of a helium atom. So we just write it as He42. Okay, beta particle is just beta with a 0, -1, and then gamma is just gamma 0, 0. Okay? So far, so good. Okay? We're not going to have time to get through this today, but we can start. Okay? All right. So we've talked about how different things are radioactive. Okay? But just because something's radioactive doesn't necessarily mean it's dangerous, or just because something's radioactive doesn't mean it produces a ton of energy. Okay? So far we've talked about two completely different things, right? We've talked about uranium-235, okay? And we've also talked about carbon-14-6, okay? Uranium-235 is the thing that powers nuclear reactors and is the core of every nuclear bomb, okay? I would not want to hold a handful of uranium-235. You'd die pretty quickly. But at the same time, it's radioactive, okay? But so is carbon-14-6. Now, there's not a ton of carbon-14-6, maybe 1 in every 1,000 carbon atoms is carbon-14-6. But if we think about it in this room right now, there are trillions and trillions and trillions of carbon atoms. So that means there's billions and billions of carbon-14-6. But at the same time, we're not dying from radiation from carbon-14-6.
What's the difference between that and like actual core?
Well, just they have more neutrons. So by putting more neutrons in the core, you make it slightly more unstable. But even though these are both radioactive, all right, uranium-235 has a lot shorter half-life than carbon-14-6. So it's this half-life that measures how long for half to decay. Okay. So each of these is going to decay on its own eventually, but uranium-235 is going to be a lot quicker than carbon-14. Okay. Uranium-235 is on the order of a couple years, whereas carbon-14 is on the order of, I think, about 5,000 years. And so the weird thing about half-life is that we can't tell precisely when one carbon atom is going to decay or one uranium atom is going to decay. We can only talk about probabilities. So your book gives the example of thorium-234. So thorium-234 has a half-life of 24 days. So if you start with 100 grams of thorium-234, after 24 days, you're going to have 50 grams of thorium-234. After another 24 days, you're going to have half of 50, so 25. Another 24 days, you're going to have another half. So you always decrease by half. And since this is only probabilities, we can never say exactly when that's going to happen. Think about it this way, all right? If I flip a coin up here 100 times, about how many times will be heads? 50, right? We can all agree on that, right? Okay, let's say by some strange, weird coincidence, I was able to flip that coin 100 times, and every single time it came up heads. Okay? Weird, right? What is the chance on that next flip that it would be heads?
Don't have a tail on it.
If it's a perfectly regular coin, it was just chance that it happened. It would still be a 50-50 chance. Okay? We couldn't say anything more than that. All we could say is that it could be 50-50. It could come up heads at 101 times. It could come up heads another 100 times. It's not very likely, but the only thing we can say each time is there's a 50-50 chance. It's the same way when we talk about atoms. If I just had one thorium atom, the only thing I could say about that one thorium atom was that after 24 days, there was a 50-50 chance it would be gone. If after 24 days I still had that one thorium atom, those past 24 days wouldn't mean anything. All I could say is that another 24 days, there's another 50-50 shot it will be gone. Okay.
Does
Now,
that work the same when it comes to like medicine if they say there's a 24-hour half-life?
I don't know.
I'm not gonna say medicine, but like I watched that movie Alex Cross, and then this man was trying to kill a woman. He gave her something that had like a 40.
Oh, okay. Yeah. And you see this in like spy stuff too, right? You know, they actually, it was just in London maybe a couple years ago, some KGB agent killed someone with a radioactive thing. Yes, and that's the same way. All right, that's a little bit exaggerated in that way because really that half-life just tells you how quickly it's going to decay. All right, but at the same time, all right, when we think about like cancer medicine, you know, use some sort of radiation treatment, they normally inject a small amount of a radioactive material that decays in, I don't know, a couple weeks, and then it's gone. And that's how we control it. All right? Now, what we'll do tomorrow, or Wednesday, is we'll spend a little bit more time on this. But if we have something like, let's try this with zinc, real quick. We still have 5 minutes. Zinc 69, whatever it is, has a half-life of 1 hour. 30. Okay? If I start with 200 grams of zinc 6930, how much would I have after 5 hours? How's the only way to do this? Well, yeah, we just do it one step at a time. So after 1 hour, I'll have 100 grams. Okay, after 2 hours, I'll have 50. After 3 hours, I'll have 25. After 4 hours, 12.5. And after 5 hours, 6.25. Okay. All right, we'll spend more time on this on Wednesday. Remember, we're going to have a quiz and go over the test. But what I want you to do is try these first problems here. Okay? See you on Wednesday. Yep. Just like every Wednesday. But it'll just be on this stuff. Yeah. But it'll just be on this stuff we covered today.
Still come Wednesday. Remember I told you I wouldn't be able to be in the afternoon.
Yeah, that's fine. Yeah. Just remind me whenever you see me, but it'll be fine.